Hello students, today we are going to discuss about Kirchhoffs laws. We have two Kirchhoffs laws. First one is Kirchhoffs current law or Kirchhoffs junction law it is also called, and Kirchhoffs voltage law. So according to Kirchhoffs first law or Kirchhoffs current law, in any electric circuit the sum of the currents entering into the junction is equal to sum of the currents leaving the junction. So here the current which are entering into the junction, summation I in, so sum of the currents entering into the junction equal to sum of the currents leaving the junction. So that the total junction current is 0. I am taking one electric circuit here. So at this junction, the some currents are entering into the junction, some currents are leaving the junction. So we will apply this law. So the sum of the currents entering into the junction, this I1 plus I2, I1 plus I2 plus I5. These three currents are entering into the junction, and two currents I3 and I4 are leaving the junction. I3 plus I4. Sum of the currents entering into the junction equal sum of the currents leaving the junction. Next we have Kirchhoffs voltage law. According to this Kirchhoffs voltage law, or it is also called as loop law. According to this law, the algebraic sum of the changes in the potential, around a closed loop is 0. Potential difference in a closed loop is 0 simply. We'll apply to apply this law. We need to know some sign convention. When you are moving across the resistor in the same direction of current, the potential difference is taken as minus IR. When you are moving the opposite direction of current across the resistor, the potential difference is taken as plus IR. If you are moving across the battery from negative to or positive to negative value will decrease, positive to negative value will decrease, potential difference is taken as minus V. Potential drop, so there is a potential drop when you move from positive to negative. So when you move across the battery from negative to positive, the potential gain will be there, potential difference V is taken as plus V. We will apply this Kirchhoffs voltage law to this loop. I am choosing this path. You need to take one path to apply the Kirchhoffs voltage law. You can choose any path. So negative to positive, the potential difference is positive. Across the resistor in the same direction of current, minus IR1, similarly minus IR2, minus IR3. So the sum of the potential difference is 0. You can write V equal to I of R1 plus R2 plus R3. So this is Kirchhoffs voltage law, and this Kirchhoffs current law is based on conservation of charge, and Kirchhoffs voltage law is based on conservation of energy. So this is all about your Kirchhoffs first and second law. Now by applying Kirchhoffs laws, that is Kirchhoffs current law and voltage law, we need to get the wheatstone bridge balanced condition. So in wheatstone bridge, four resistances P, Q, R, S joined to form a quadrilateral across the arm BD. Across the arm BD, we connected this galvanometer having the resistance G, and across AC we connected a battery of potential difference or EMF E, battery of EMF E. Now by applying Kirchhoffs current law at junction B, so here the current I which divides here at A divides into I1 and I2. At junction B if I apply, so here is the current is I1, this I1 divides into galvanometer current IG and I3. So by applying Kirchhoffs current law at junction B, I can get some of the currents entering into this junction at B, which is I1 which is equal to some of the currents leaving the junction I3 and IG. I1 equal to I3 plus IG. Take this as equation number 1. Again we will apply Kirchhoffs current law at junction D. At junction D you can see here the current IG is coming from here, and I2. So in this current is I4, I3 here and I4 in this. At junction T, the sum of the currents entering into the junction I2 and IG which are entering into the junction, and I4 is leaving the junction. I2 plus IG which are entering into the junction, which is equal to I4. This current is leaving the junction. So take this equation is equation number 2. Next we will apply Kirchhoffs voltage law. Kirchhoffs voltage law, we apply to the loops. Any closed loop we can take. I am taking a closed loop A, B, D, A. So A to B, we apply the Kirchhoffs loop law to A to B. I am moving the same direction of current across the resistor. This is taken, potential difference is taken as minus I1P. Again from B to D, A to B is over, B to D, again the same direction of current, minus Ig into galvanometer resistance G. From D to A, I am moving the opposite direction of current across the resistor R. This is taken as positive plus I to R. This total potential difference is equal to 0. If I want, I can write I1P plus Ig into G, which is equal to I to R. Take this as equation number 3. Next, applying Kirchhoffs voltage law. We will apply Kirchhoffs voltage law to the second loop here, B, C, D, B. B to C in the same direction of current, minus I3 Q. C to D, opposite direction of current, C to D, opposite direction of current, plus I4S, resistance S. Again, opposite direction of current, D to A, opposite direction of current I am moving, plus Ig into G equal to 0. If I want, I can write I3Q, which is equal to I4S plus Ig into G. Take this equation as equation number 4. The bridge is said to be balanced. So we need to get the balanced condition of wheatstone bridge when galvanometer current Ig equal to 0. This galvanometer current Ig equal to 0. When galvanometer current Ig is 0, the bridge is said to be balanced. So to get the balanced condition of wheatstone bridge, I am applying I am writing this Ig, galvanometer current Ig equal to 0. So we will substitute this Ig equal to 0 in all 4 equations. Applying to the first equation. From the first equation you can write, if you put Ig equal to 0 in equation 1, what will we get? Ig equal to 0, then we left with I1 equal to I3. So equation 1 implies I1 equal to I3. Equation 2, if you substitute that value Ig equal to 0 in equation 2 implies Ig is 0, I2 equal to I4. I2 equal to I4. Applying to the third equation, the Ig equal to 0, putting the Ig equal to 0 in third equation, I1P equal to I to R. I1P equal to I to R. Equation 3 implies I1P, which is equal to I to R. I to R. And substitute I is equal to 0, fourth equation, you will get I3Q equal to I4S. Name this equation as 4 equations of 5, 6, equation 7 and 8. Now divide equation 7 by equation 8. Equation 7 by equation 8 we get right hand side I1P by I3Q, which is equal to I2R by I4S. Since I1 equal to I3 and I2 equal to I4, we can write P by Q equal to R by S. So this is the wheatstone bridge balanced condition.